So, in this session we are going to study about fluid mechanics. So, the fluid mechanics is divided into fluid statics and fluid dynamics. So, let us first talk about fluid statics. So, fluid statics, so let us see what is a fluid first. So, let us define a fluid. So, when I say fluid, I mean with substances except solid, that may be liquid or gases. So, when I say fluid, that means I want to define my fluid ideally. So, a ideal fluid is a substance which yields to the slightest effort. So, if I apply a small force, this fluid will yield. So, it is a substance which yields to the slightest effort. So, in other words, it cannot withstand shear stress. So, it cannot withstand shear stress. If you want to produce a shear stress, we can't do that. So, in order to understand what is shear stress, you see, if we take a piece of paper, we can tear it. So, a solid can be teared, but a gas or a liquid cannot be teared. We cannot tear a liquid. So, that is why, because it cannot withstand shear strain. That means a substance, so the substance which responds to the shear strain, that response is through a shear strain. So, if you apply a shear stress, the substance responds by producing shear strain. So, we can also say, so does a fluid does not produce a shear strain. So, telling that it cannot withstand shear stress means it does not produce a shear strain. So, this is what a fluid is. That means, that is i.e. there is no relative motion between different fluid layers. As a result, so the fluid layers will not glide among themselves, an ideal fluid layer. Thus, so a free body kept inside a fluid experiences a net normal force, because the liquid cannot produce a shear force. So, it applies always a normal force, no tangential force along a free surface or a free body kept inside a fluid. So, this is the definition of fluid. Now, so thus we see that the force is always normal to the surface of a free body. Thus, we can define at each and every point inside a fluid a property called pressure, which is a scalar quantity. Let us see how to define the pressure inside a fluid. Now, let us define fluid pressure. So, inside a liquid, suppose I have placed a area, this is the area and this area is dA, this is inside a liquid. So, this liquid is like this and I want to define the area, the pressure for at this point. So, what I have done, I have taken a small area, elemental area dA. So, how we defined the fluid pressure at a point is defined as the ratio of the normal force to the area in the limit of area tending to 0. So, you see there is a normal force acting in this, that is, suppose I say dF. So, we define P as limit of delta area tends to 0. So, suppose let us first define this not by dA, let us write it by delta A, and let us write this by delta F. Previously I wrote by dF, let it be delta F. So, now I am taking the limits. So, it will become delta F by delta A. So, we can also write this as then dF by dA, but this is the basic definition. So, let us work with this definition of pressure. So, when this area element is diminishing small, this delta L will be called dA, and that force, the normal force, let us call this normal force as dFn. So, this is the pressure at a point defined at. You see, it seems that we define pressure, but actually dF normal becomes P into dA, and so total normal force becomes integral P dA. So, the total force will be the pressure into the total area. Suppose the pressure is constant, so P will be there and that will be delta A. So, you see pressure is a scalar quantity. Pressure is a scalar quantity. Its SI units is Pascal. 1 Pascal is equal to 1 Newton per meter square. So, the SI unit of pressure is Pascal and 1 Pascal is 1 Newton per meter square. So, we see that the pressure is a scalar quantity and the total force acting on this area, on any area, will be integral P into dA, and we define pressure, fluid pressure, as the force acting per unit area, and technically that force is small, this area is small, that means limit delta A tends to 0, delta F by delta A. So, this is how we define pressure. Now, pressure is measured with the help of manometer. So, pressure is measured by a device called manometer. So, in manometer we use the height of a liquid column to measure the pressure of anything. So, the manometers which are used to measure the manometers which are used to measure atmospheric pressure are called barometers. So, we have a specialized manometers to measure atmospheric pressure and we call it barometers. So, these are also manometers. Now, we generally express the pressure with respect to vacuum and sometimes with respect to atmospheric pressure. So, when the pressure is expressed with respect to atmospheric pressure then it is called gauge pressure, and when it is measured with respect to vacuum, then it is called absolute pressure. So, you can see P absolute can be written as P atmospheric plus P gauge pressure. So, this is how the absolute pressure, atmospheric pressure and gauge pressure are related. So, we have our atmospheric pressure, one atmospheric pressure is equal to, we write this as 760 mm of Hg, that is 76 centimeter of mercury, that on calculation comes out to be nearly 10 to the power 5 Pascal, that is Newton per meter square. So, this is the atmospheric pressure. Now, let us see, once I define a pressure, let us see Pascal's law. What is Pascal's law? According to Pascal's law, the fluid pressure at a point is the same in all the directions. So, now let us see Pascal's law. According to the Pascal's law, the pressure at a point in a static liquid is the same in all directions. So, the fluid must be at rest, and so at the point, whether it is in this direction, this or this, up, down or any direction, the pressure is going to be the same. So, you can see it is a direct consequence of the fluid pressure to be normal to a free area. So, you see it is a direct consequence, since the fluid pressure is always normal to a free area. So, automatically the pressure is going to be the same for at any point in any direction. This is what Pascal's law is there. So, based on Pascal's law, we have a lot of engineering equipments like hydraulic pressure, Brahma press, hydraulic presses, all these things were on the principle of Pascal's law. Let us theoretically prove it, Pascal's law. So, in order to prove this, consider a small tetrahedron inside a static fluid. So, imagine that there is a tetrahedron. So, now let us imagine a tetrahedron which is like this, and let us name it the A, B, C, D. These are the, so you can see A, B, C is a face on which there is a force called, the pressure P is acting on this here, and on this the pressure is P dash. So, consider a small tetrahedron inside a static fluid. Let P be the pressure on the face ABC, on the triangular face ABC. A tetrahedron has triangular face and a different pressure P dash on the face ACD. So now you see here, this is a face on which there is a pressure. So the force on ABC, so the force on ABC will be actually that pressure into area of ABC will be P into area of triangle ABC. So now let us, this is the force on ABC. So this force is F. Suppose I denote this force by F, and let us suppose this direction to be X. So what we do, we draw this triangle. You see, this is the area which is the projection of area of triangle ABC on this, and ACD area will also have the same projection, that is, suppose I say E. So Fx, let us calculate what is the value of Fx. So the projection of this area on this is this. So it will be P into, this is F is P into area of ABC, and Fx means projection of this area on this. This is a scalar quantity, P into area of triangle AEC. So this is Fx. Now you see, so this is P. Now let us see F dash. F dash is equal to the force on ADC, force on ADC, that is equal to P dash into area of triangle ADC. So now if I want F dash x, then this is P dash into area of triangle AEC. Again I have to take the same cross section. So if this pressure is P dash and this area is there, it will have a normal force, and if I want the same projection, same along x axis. Now you see, this tetrahedron is in the liquid, and it is, you see, there is no net force in this direction. So thus this area and this area is same. So since Fx is equal to F dash x implies P into area of triangle, that is AEC is equal to P dash into area of triangle again AEC. These cancel, so P is equal to P dash. Thus P is equal to P dash. That means if a tetrahedron is there and it should be in equilibrium inside a liquid, then P must be equal to P dash, and this is not a special direction, x is arbitrary. That means the pressure is this direction, and we can have this direction also. So P is equal to P dash is equal to P double dash. Thus the pressure is the same in all the directions.